Okay, now we are recording this lecture, and today we'll talk about, we'll continue our last lecture to share about the interactive proofs, because in our first lecture, we just read the introduction of interactive proofs, the definition and the properties about the soundness error and also the completeness error, the delta C and delta S. And today we'll be learning together about one of the most important protocols, the sum check protocol in interactive proofs. So today, let's look at the 4.1. Okay. The sum check protocol. We'll go to the details. To say how the prover sends his claim to the verifier and how the verifier verifies it step by step. So first, suppose we are given a variate polynomial g defined to our final field. Okay, note here. Our sum check protocol will work over the final field. So I think we all have the basic knowledge about the algebra. Because final fields, we can just think of it as we have finite numbers. For example, 0, 1, 2 to n minus 1. So finite fields means we need to mode. Okay, we need to mode n. Okay, that means we need to mode. So the numbers are finite. And the purpose of the sum check is for prover to provide the verifier with the following sum. Okay, here we can see the following sum. The g is the polynomial, and there are v variable b1 to bv. Okay, for each variable, there should be the input, and let's say the input is here. b1, b2, and bn, and the range of their input is limited to only two values, 0 or 1. So it's very limited range, only 0 or 1 is binary. And so summing up the evaluations of a polynomial over our Boolean inputs, all Boolean inputs. So for b1, which was 0 or 1, and for b2, which was 0 or 1, and until bv, we also choose 0 or 1. And we just substitute this variable with 0 and 1 and add them together to get the sum of this polynomial. So it's like a control task. It's like an task with some specific intention. It seems like it has only a very limited utility, but later we will find it is one of the most important protocol. Okay, here let's look at this remark. In full linearity, the sum check protocol can compute the sum for any b belongs to f. But most of the applications covered in this survey we only require. So here we only talk about the range of the input is 0 and 1. And what does the verifier gain by using the sum check protocol? Because if the verifier need to compute this h again via this equation, yes, if the verifier computes this h via the 4.1 equation, it will be very costly, ineffective, because it needs the two-way evaluating g at two-way inputs. But two-way is an unacceptable large runtime for the verifier. Yeah, so it is very time wasting. But under the sum check protocol, we will prove that the verifier's runtime is much less than the two-way. Okay, let's move on. We can evaluate. Okay, we can evaluate GR1 to RV for randomly chosen vector. Okay, we can recall our last lecture because we mentioned that for the prover and verifier, as prover sends the proofs. As verifier sometimes sends the since there are because verifier has the randomness, you can choose the vector with the randomness. So this R is the random number. Okay, so in the subtract protocol, we will evaluate this polynomial for a randomly chosen vector with a single query to an oracle. This oracle is it has the oracle to G because it will query this vector on this G polynomial. Okay, a self-contained description. Yes, so this is the most important part of this lecture. We'll introduce the whole process of this subtract protocol. Okay, let's look at this at the start of the protocol. The prover sends the value C1 claimed to equal to the value H. H, remember, it is the equation, the sum equation defined in this 4.1. In the first round, go here. Here is our H. Okay, is the sum of this polynomial on each variable. Okay, in the first round, P sends the univariate polynomial Gx1, G1x1. We call this G1x1 claims to equal. So the first round, P claims that G1x1 should be equal to this sum. Okay, to this sum. So here we can look at this formula. G, because initially it is x1, x2 to xv. There are v variables, but here we just use x1, the capital X, okay, the capital X to replace the small x, and then we check that C1 should be equal to G1 0 and G1 1 because so what's the logic of this formula? For G1 we know for G1 it is this equation, and only x1 is the univariate polynomial. So this means only the capital X1 is the variable. So it is the single variable function. So here, but its input is limited to 0 and 1. So for this univariate polynomial, this is all the outputs it can obtain through the input 0 and 1. So we just so the verifier just checks the all the outputs, and also G1 is the univariate protocol is the univariate polynomial of degree at most. Okay, this notation means the degree of this polynomial in variable xg. Okay, so for this one it is G1x1's degree. Okay, it is G1x1's degree. Okay, let's make it clean. Okay, so after that, in the jth round, okay, the last round will be the Vth round. Now we in the jth round, the prover sends to verifier a univariate polynomial. So now it is not only G1x1. Now it upgrades to JJXJ, claim to equal. Yeah, so the same, similar to our first formula, but the difference is here for previous parallel to xg. Okay, parallel to xg. because after xj there is a small xj plus 1 to the xv, but parallel to xj, the values should be fixed to we can use the here we see we can evaluate verifier can evaluate R1 to RV for randomly chosen vector. So this R so these R's are sent by the verifier, and these R's will be used to fix the variables parallel to xj. So here should be R1, R2, 2R j 1, and then here comes the xj. So these values are obtained by the verifier. So verifier fix these values. And then after the verifier receives the polynomial, the claimed polynomial, verifier checks that jj is the univariate polynomial of degree at most. So it just ensures the degree of this univariate polynomial. There's no problem, I think. And that j minus 1, r minus 1 should be equal to jj0 plus jj1. So it is very familiar form because we just saw it before. Here, c1 should be equal to j10 plus j11. So here the c1. Okay, here it uses the c1. C1 is the first value that proves since it is claimed to equal the value h. But after the first round, we will not use the C1. We will use for this round, we will use the j minus 1, r j minus 1. So for completeness, we can look why this formula should hold. Because okay, here for jj polynomial. So what is the form of the jj polynomial? Okay, here let's have a look. For jj, it is a form of this formula, of this. So it has only one variable, that is xj, and xj its input should be limited to only two values, 0 and 1 as binary. So the only possible outputs of this univariate polynomial is j0 or j1. So the verifier just plus this one, plus these two outputs. But what is the result of this sum of the two outputs? Because its result should be equal to j minus 1, r minus 1. Okay, because in j minus 1, r j minus 1, is also the form of this formula, because it is the first time that for this polynomial, this variable xj minus 1 is given the value of rj minus 1. Okay, so after this xj minus 1 is given by this rj minus 1, so only others can be the variable. And for this jj protocol, for this jj polynomial, the xj is the variable, is the univariate variable, and it has the input 0 or 1. So after we take these two inputs and add them together, we can obtain the parallel. The parallel is the parallel value. So I think this is the logic of this formula. And verifier will reject if this doesn't hold. And then verifier chooses the random element Rg for fixing the value of Xj, because it verifies this univariate polynomial holds. So the Xj can be fixed by this Rg, randomly chosen by the verifier. So now we can see this logic. It's just the step by step in each round. For each step, first the brewer sends the univariate polynomial, but in every round, polynomial is different from the pair one from the previous round. So in the last round, the final one in round V, brewer sends to verifier a univariate polynomial JVXV claimed to equal to this one. And now we're familiar with this because now the XV is the last variable for this polynomial, and verifier checks that JV is the univariate polynomial of degree at most degree Vg. Yeah, it is the notation of the degree, rejecting if not. And also checks that it also will use this formula, Gv minus 1. So it is the parallel polynomial, and we'll fix the xv minus 1 with rv minus 1. It should be equal to jv 0 plus jv 1. Because for the left-hand side of this equation is a value, and this value is fixed by the rv minus 1. And rv minus 1 is located in the x v minus 1's location. Okay, it is to replace the x v minus 1. But for the right-hand side of this equation, the 0 and 1 is to replace the location of the xv. Okay, so yeah, it is to replace the location of xv. But we take both the output and add them together. So there's no variable on the right-hand side, because we have already taken out the outputs. So now it is just the value. So value equals value now. So after the V runs, the verifier chooses a random element RV, and the value is G, R1, R2 until RV, to RV, with a single oracle query to G. So there's only one oracle query, because prior to this, we can say before there's no query to G. There can be no query to G, because only here it mentions a single oracle query to G with R1, R2 to RV. And verifier checks that GVRV should be equal to JR1, R2 to RV, because GVRV, there's only it is the univariate polynomial. It has only one variable, that is xv, and now we just fix the xv by the rv, and so now it is equal to the original polynomial with r1, r2 to rv and this whole vector. I think it is very understandable now. Okay, let's clean it. And after it, if verifier has not yet rejected, then the verifier says this and accepts the proof, and then this protocol completes. Okay, now let's look at the detailed description. Because before a detailed example, we also need to understand more detailed logic of this protocol. So first, at the start of the first round, the process polynomial. Now we are very familiar to this process, and the polynomial g1 x1 is claimed to equal the polynomial s1 x1. Here we have another s1 x1. So what is this? It is defined as this formula. Okay, we can see this. Just replace the small x1 with the capital X1. And for others, we should add them together because the small x2 to small xv, they are not variables for this univariate formula. Only the big x1 is variable because there is no value for the big x1. It is, it can be changed. It is a variable. But for the others, they have the range of values can be taken to this polynomial, and they can be taken using 0, 1, 0, 1 for each location for small x2 to small xv. And the s1 is defined to ensure that h should be equal to s10 plus s11. We still remember that c1 should be equal to j10 plus j11. Okay, we still remember this. So here we just use h and s10 and s11. So this should be in short. This h should be equal to s10 plus s11. Okay, let's see what happens after this. Okay, accordingly, verifier checks the C1 equals J1. Okay, let's see here. Fluorescence value, C1 claimed to equal value H. Okay, fluorescence the value C1. Because H is defined in the equation. Okay, in the equation 4.1. In this big equation is the sum of all possible outputs. If the sum of all possible outputs. So H is the final sum. And C1 should be equal to H. It is claimed by the prover, and prover sends this value C1. And verifier should check the C1 sent by the prover should be equal to J1, because J1 is polynomial J1 is also sent by the prover. So it is just verified by the verifier. There's nothing created by the verifier. Okay. Okay, the verifier checks that J1 and claimed answer C1 are consistent with the equation 4.3. Yes, because the J1, as we just mentioned, C1, J1 are sent by the prover, and C1 is the claim. And J1 is also claimed. C1 is claimed to equal H. C1 is claimed to equal H, and J1 is claimed to equal S1. So accordingly, as verifier checks the J1 and C1 are consistent with the equation. And let this degree denote degree of variable I in the polynomial G. if the prover is honest, the polynomial g1x1 has degree, has this degree. And here, g1, how can g1 be specified? Because it is a polynomial. So it can be verified, it can be specified with is d plus 1, d is the degree of this g1. So it can be specified by d plus 1 elements, also field elements. So why? It's because it is very simple problem. Just if you have a polynomial with degree d, for example, xd, gx equals xd plus xd minus 1, axd, bxd minus 1 plus c xd minus 2, okay, maybe to z, zx the 0, zx to 0, and there are many. So how can this gx be identified? Because there are many coefficients, so we need to ensure one by one. So we need at most. So how many elements do we need at most? It is d plus 1 because there are at most d plus 1 coefficients. Okay, coefficients. So we need d plus 1 elements. So d plus 1 pairs, for example, x 0, y 0, x, okay. X0, gx0, and x1, gx1, and xd, gxd. Yes, and we can combine these equations to get the a, b, c, and all the coefficients. Okay, that is very explicit. Okay. Oh. Okay, now. So the first value can be specified as by the elements, and the elements can be 0, 1 to degree. They are right, d plus 1 elements. So it can identify a polynomial g1. And the rest of round 1, after the g1 is sent by the prover, and it is claimed to equal polynomial s1. The idea of the sum check protocol is that verifier should probabilistically check this equation of polynomials holds by picking the random value r1 that belongs to this field f, and confirming that g1 should be equal to s1. Yeah, this is the must. Clearly, if g1 is as claimed, and this inequality holds for all r1, because these two polynomials are equal to each other. So for all r1 chosen by the verifier, this equality holds. It's a must. And so the problem is if these two polynomials are distinct. So what probability? What probability that for the R1 chosen by the verifier, this equality also holds? So this should not happen. But what is the probability of this fault? So it should be if G1 is not equal to S1, then with probability at least 1 minus this d over f, the card f. That means the number of the field. So why we use the 1 minus the d over this f? Because if these are two distinct polynomials, so how many r's will help hold this equality? So it's like solving an equation. So we can think of this question like this. It's like solving an equation. It's very simple because so what's the dimension of this equation? Okay, what's the dimension? We can just regard it of g1 minus s1 equals 0. Okay, and the r1 will be x. So it's an equation now. So what's the dimension of this? Its dimension is just the d. Okay, the degree, just d. We use d to represent. So just d. So how many answers to this equation? At most. So at most it is if its degree is d. So there will be d solutions to this equation at most. So the d is here. Okay, here's the d. So this will be the probability. Okay, because the number of the range, the number of the field is card f. So d over f will be the probability that probability of the solutions that make this equality holds. So here we choose 1 minus this 1. Okay, so just solving this equation. At least the 1 minus this d over f, the equation fails to hold. Okay, the equation fails to hold. So it is highly likely that the verifier can verify this equality, because the probability is very high. At least as long as the f is number of f is very high. And so the card f should be much bigger than the degree. Okay, so this is the requirement. Let's say the remaining issue: can we efficiently compute both g1 and s1 in order to check the equation holds? So let's say this one. Since P has proper sense verifying an explicit description of the polynomial g1, yes, the g1 is sent explicitly. It is possible for the verifier to evaluate g1 r1 in the degree time. But evaluating s1 r1 is not. It's very difficult since s1 is defined. So how does s1 be defined? Let's say s1 is defined as a sum. Okay, s1 is the sum over 2 to v minus 1 evaluations of g. Let's say the definition of s1. Okay, here is the s1. So if we compute this again, it is very time wasting. This is only a factor of 2 or smaller than the number of terms, because for calculating h, there should be O2 okay, for calculating h, because there are v variables, and for each one there are 2 possible inputs, there are 1. But for this s1, x1 is a variable, and there will be no inputs for this one. But for the remaining x2 to xv, each one has there are 1, so there will be 2 to v minus 1 runtime. So only a factor of 2 smaller than calculating h. Okay, that's the logic of this one. It is also to time costing. Okay, so fortunately equation 4.2. Okay, let's see the 4.2. Oh, where is 4.2? Okay, here. Let's clean it. Okay, 4.2 is the definition of S1. Expresses S1 as sum of the evaluations. So now we look at this S1 again. So it looks like we can think of this as another sum check problem. If the v function, we will not use v, we can use h function x2 to xv. So it is another sum check protocol because we can just neglect this x1 at this time to calculate another sum check polynomial. So here, exactly the type of expression that the sum check protocol is designed to check. Okay. So the polynomial being the R1 can be fixed, but the x2 to xv are v minus 1 variables is defined, or this v minus 1 variables. So rather than evaluating S1 R1 on her own, as we instead recursively applies the sum check protocol to evaluate S1 R1. So it's just a recursion. So let's see the recursive description of round 2 to v. This protocol proceeds in the recursive manner with one round per recursive call. Let's say this means in round G. Let's look at round B. The variable xg gets bound to a random field element Rg chosen by the verifier. So in round G, the xg should be fixed by the Rg. And this process proceeds until V, the Vth round, where the prover is forced to send the polynomial GV xv claimed to equal to SV. So how can verifier check? Verifier will check that JVRV should be equal to SVRV because the RV is randomly chosen by the verifier. So this randomness help check this equality holds. And there's no need for further recursion since the verifier is given our size to, yes, because we remember that after the V rounds of this protocol, then the last time verifier is given oracle size to J polynomial, and verifier can evaluate. Yes, the verifier can evaluate SV RV should be equal to J R1 to RV because the letter is JV RV. Okay. So there is no need for the further recursion because we can evaluate this one through querying to J. So this is the last step of this protocol. And let's look at the iterative description of the protocol. Okay, unpacking the recursion described above, here's the equivalent description of what happens in round J of some check protocol. So these two, the first one is the recursive description. Now it is iterative description. These are the two perspectives of understanding this protocol about what happens in round J. Okay, let's look at this one. At start of round J, variables x1 to xj minus 1 have already been bound to run fixed elements. The payroll variables have been bounded to R1 to Rj-1. This J-1 random values. And then the prover sends the polynomial JJXG and claims that, okay, we have looked this equation before. And then the verifier compares the two most polynomials by checking this and rejecting otherwise. The verifier also rejects if the degree is too high, because in the description of the protocol, we also should ensure that the degree should be correct. And after the ensuring of degree, the verifier should choose value, random value RG, and sends the RG to the prover. And in the final round, the prover has sent JVXV, this polynomial, this univariate polynomial, which is claimed to be this one. As the verifier now checks that JVRV should be equal to this one, and this one can be queried to J by the verifier. So if this check succeeds, then the verifier convinced. The verifier is convinced that this holds H equals to J10 plus J11, so there will be no problem. Okay, let's look at this very vivid, very useful example execution of some check protocol. So here is the polynomial. J its degree is d equals 3. Okay, d equals 3. Okay, here I'm wrong. We can use this notation. Okay, because there are 3 variables, so what is the degree 1 for J? Degree 1 means the degree of J1x1. Okay, the degree of J1x1. So to compute J1x1, we need to sum. Okay, we need to sum J(x1) and small x2, small x3 with all the possible inputs. Yes, x2 belongs to 0, 1, and x3 belongs to 0, 1. Okay, we need to compute the sum to get this J1x1. So the degree is not as easy as 3. The sum of J's evaluation. So what is the sum? The sum should be all possible inputs. As we take all possible inputs to this polynomial and to get its result, and H should be 12. So how many possible inputs? How many possible combination of inputs? Just x1, x2, x3 can be equal to 0, 0, 0, 0, 0, 1, and 0, 1, 0, and 0, 1, 1. So 3 variables, so 2 to 3 equals 8 possible combinations. So we just take this 8 inputs, these 8 factors to this polynomial and add them together to get this 12. Okay. And here, what is the J1x1? When the sum-check protocol is applied to J, the only the prover's first message. Okay, first we should compute the S1. Okay, S1 is just like what we said. The X1 should be fixed and the others should be summed together with all possible inputs. And we can get this S1 equal 8x1 to 3 plus 2x1 plus 1. So what is degree? Degree is 3 now. Now it is 3. Okay, and due to the process of the protocol, the verifier should check that. Yes, it should check S2, okay, S10 plus S11 should be equal to C1, so it should equal 12. Okay, it should equal 12. So if this holds, then since the prover R1, suppose the R1 is 2, and it's a random value, and the honest prover would then respond with the univariate polynomial. Okay, so after in the first round, it sends S1, X1. Now it sends the S2, X2. Okay, with all possible inputs except X2. Now we get the S2, X2 equals 34 plus X2. Now its degree is 1. And then the same step is the verifier checks that S1 0 plus S1 S2 0 plus S2 1 equals S1 R1. Okay, this is the Pyro value. Because for the Pyro value for S1 R1, for X1 R1, X1 is the variable. But for X2, X2 is the variable. But X2 now is fixed by all possible inputs. So these two values should be equal to each other. Okay. So round by round until the okay, let's look at one round because we can verify some of its calculation. For example, S1 S2 X2 equals 34 plus X2, and we can verify the S1 R1, and S1 is this polynomial and R1 is 2, so we can use 8 times 2 to 3 plus 2 times 2 plus 1 should be equal to 8 times 8, 64 plus 4 plus 1, 69. And so how about this one? We should input 0 and 1 respectively, and to get 34 times 34 times 1 plus 34 plus 1 should be equal to 69 as well. So they are the same. Okay, no problem. So after the S3, the S3 has been sent, the verifier confirms that the same equation as before, S3 0 plus S3 1 should be equal to S1 R1. So this is the last step because only 3 variables here. Okay, so this is the last step. And after this S2 R2, because there's no further iteration, and the verifier picks the random element R3, and the R3 is sent to the prover. Suppose R3 is 6, Okay, this R3 is now sent to the provider. The verify just confirms that S3, R3 is because in the parallel step there is S2, R2. Because for S3, R3, we do not have the S40 plus S41. Okay, we do not have this. So we can, so in this last step, we should query to G to verify whether R3 equals G236. This is just G R1, R2, R3. Okay. Yeah, so this just follows our description of the subtract protocol. So it should hold. Okay, this is the step and the example of the protocol. In the next video, we'll talk about the soundness and completeness, and also the how to compute the costs. Okay, I think because this is my first time to record this video about the zero knowledge proof, I think it is a little bit time costing in detailing some concepts, fundamentals. So I will arrange the time in next lecture. Okay, thank you for listening. This is for today's class.